Alrighty, everybody, let's begin neutralization part 2. Hey. Marty Steinblum.
The troublemaker.
Hello. Hi. Now we got the troublemakers out of the way.
Okay. This is your last chemistry
Of the year.
PowerPoint of the year.
Ever.
Praise God. Don't say ever.
Hopefully, at least for chemistry. Kevin, get out of here.
Kev! Where's Monday?
What is he supposed to be in?
Yeah, go get him. Go whoop his buns.
Bitchin? Oh, is he lecture?
No, it's Spanish, I think.
First bleacher. Marty.
Yeah, but
We're going to call and
The names are fine.
Not next week.
Is he still there?
And then we have.
Honestly, what idiot.
It is
Titration, seriously, let's pay attention.
I would decide that.
Okay. What a titration is, if you go to college and you have any desire to do any kind of pre-med, any medicine, any kind of medical field, you will have to take regular chemistry in college and organic chemistry in college, and you will do tons of titrations in college. Okay. What a titration is we know that acids and bases do what to each other? They neutralize, okay?
Yeah.
So you can use that concept, you can use the idea that acids and bases neutralize each other, and what you then can do is, let's say you have some volume of an acid, you know it's HCl, but you do not know the concentration of it, okay? What you could do then is you could little by little add a base of a known concentration until their pH turns to 7. At a pH of 7, what's true?
Neutral.
It's neutral. That means all of your base neutralized your acid. Well, then you could figure out how much volume did I use and what was the concentration of my base that I added, and you could do a little bit of math to figure out exactly the concentration of your unknown acid. Yep. And that equation is really just this, which you're going to get in a little bit. It's the molarity of your known times the volume of your known will be equal to the molarity of your unknown, that's a U, times the volume of your unknown. Okay?
That looks like Boyle's law.
It's an inverse relationship. Okay? So for example, if I had a acid that was 1 molar concentration, and I had a base which was 0.5 molar concentration, I would need twice the volume of the base to neutralize the acid. Right? That makes, I'm using simple numbers, right? Not always are you going to get a nice ratio like that. But if I have 0.5, and let's say it took me 100 milliliters, and I wanted to neutralize that with a 1.0 acid, what would have to be the volume that I would add? 50. And that should make sense, right? This is twice as concentrated, and so therefore I only will need half as much volume to neutralize my other guy. Okay? Because remember, what is the hydrogen, or sorry, what is the thing? Give the answer.
Hydrogen.
Well, what does the acid give off?
Hydrogen.
Hydrogen, and it usually gives it off in a 1-to-1 ratio, right? And what does the base typically do? Gain that hydrogen by giving off its OH, right? Now, however, some of the strong bases can give off 2 times the hydroxide, so we do have to take that into consideration later on. Okay? But normally, both give off at a 1-to-1 ratio, so if you know the moles of one, you then know it's the same amount of moles of the other that you have to use to neutralize it. Okay? This actually can be really painful, because I remember in college, we had to when we would do this, we would try to neutralize the acid. At the beginning, we could add a decent amount of acid or a decent amount of base to start neutralizing it, but near the end, the pH towards close to the equivalence point changes really quickly, and so you have to put 1 drop in and then measure the pH, and then 1 more drop, measure the pH, and then another drop and measure the pH, and then another drop, and it was like you would literally take a 3-hour lab, just drop, rate, drop, rate,
Whoa.
drop, right? And it was kind of fun because we a lot of times use an indicator and you would see the color change at that pH, which is kind of cool, but it was pretty painful, to be honest. Okay, so when we would do this in the lab, we would get what was called a titration curve. It basically just shows how the pH is going to change over time as you add that base or acid to neutralize the other. And I'm going to show you an example of it on the next slide. I don't know if you guys have it in your notes here, if not. Okay. So here's an example. So let's say I started here, right? Okay. pH is what? What does that tell you?
Very acidic.
Very acidic. So the thing I'm trying to neutralize must be a acid. Did you say base?
No.
Oh, I thought you said base.
Yes.
Okay. It's an acid. Okay? And notice that over time the pH starts to rise, which means I must be titrating it with a base. Okay? So as I'm adding base, that acid that I have in there is getting neutralized, and you're starting to see the pH start to rise. Because if I have less H in solution, then I have a higher pH, correct? Right? Because the pH is dependent upon how much what you have. Hydrogen. It's called negative log of your hydrogen, right? pH. Okay? Now, remember how I said that you would start adding one drop at a time?
Yeah.
And that's because there comes a point where one drop will change the pH.
A lot.
Okay? That's a great question.
Is that a constant for that?
What do you mean constant?
Like that one drop? They're saying it's the same for everything.
No. This is going to be what a titration curve looks like for a strong acid with a strong base. Because once you get close, like one drop, since it completely dissociates, will change the pH pretty significantly close to the equivalence point. If I were to do a pH curve of like a weak acid with a weak base, it would not be as dramatic. Because a weak acid and a weak base don't completely dissociate. So when you add a drop of a weak acid or a weak base, it's not giving off as many hydrogens. Does that make sense? And so if it's not giving off as many hydrogens, you're not going to see the drastic pH change.
It's kind of like,
when it gives off its last hydrogen? Is that now what it says?
Yeah, sure. You can look at it that way.
so remember, it's kind of like this, like two really strong, and it's like
Sure.
in comparison to like a weak one, it's like
I'm not sure which
like
one to show you.
this is a strong base, a strong acid, they're like button heads, and then it's like one drop's like
Sure. You can look at it that
and
way, I
it's
guess.
like weak, it's like
Does that help you guys at all?
what? That's so relatable.
It's like me and
Yeah.
wrestling versus me.
You gonna
Now what they're
Yeah,
showing
yeah.
you here, what they're showing you here is a couple indicators. Remember, what does an indicator do?
shows pH, indicates.
Okay, it changes color at a certain pH range. Okay, now honestly, if I wanted to find the pH, I wanted to know where the equivalence point was, or a pH of 7. Neither of these indicators would probably be the best choice. Because I'm going to see a color change with this indicator about right here, correct?
No.
That's about 9.4, right? That's not going to probably help me figure out where the pH is 7, is it? Okay, and I did not know bromocrystal green had, well, I'm guessing it's just one color change. It just becomes green before it becomes blue. But you'd probably say it'd be about there, which again, that's probably not going to tell you where the neutralization point is, or what we would also call, I haven't defined it yet for you, it's also called the equivalence point. Right? It's where your acid and your base are equivalent. Okay? So this is kind of what I was showing you earlier. Right? I've got, it required 100 milliliters of 0.5 to neutralize 50 milliliters. You see how it hits a pH of 7 at 50 milliliters? Okay? That's what I was trying to state earlier. Okay, this is more concentrated, so it doesn't require as much volume to neutralize. Okay, and this is going to require more volume because it's not as concentrated. Okay? So that's really the gist of a titration. is taking and trying to figure out some unknown concentration by using something you know and your understanding of neutralization. That's called the equivalence point. We'll define that later. But... oh, there it is. So here's some just kind of vocab words more than anything. Equivalence point specifically means when you have a pH of 7, and what do we know is true about a pH of 7?
Neutral.
Okay, which means you have the same amount of H as you have OH. Okay, that's called the equivalence point. The end point is specifically talking about when you have an indicator in your solution. Remember, an indicator changes colors at a certain pH depending upon what kind of indicator you're using. When that color change happens, we say that's the end point of the indicator. Let me go back and explain. So don't get equivalence point and end point messed up. Okay, where do we see a color change here? About where?
9.
About a little over 9, right? That would be the end point for that indicator. Is that the equivalence point?
No.
No.
Wait, what are you saying? Isn't that whole square white?
What are you looking at, girl?
This is pink.
I can't, it looks one color to me.
Wow.
Well, don't use that indicator.
She's lying.
Don't use that indicator.
It's probably the glare or
Use the
something.
line.
Yeah, here. So this would be the end point for this
It
indicator.
still looks the same.
Okay?
Shut up.
But we can have different indicators, right? So
Yeah.
each indicator has a specific endpoint. Do you think there's an indicator that has an endpoint really close to the equivalence point?
Of course.
Yeah, there is indicators that have endpoints really close to the equivalence point. Just not these two. Okay? There's different reasons why we would want an indicator to be not at the equivalence point. Let's say I specifically wanted a solution to be 9.4-ish pH. And I wanted to create that solution. I would have used that indicator, phenolphthalein, to be able to figure out when the pH got to 9.4. Or I could probably just use a pH meter, that'd probably be the best way. But an indicator could do
Why would you choose?
because in their acid form, they're one color, and in their base form, they're another.
But like none of it comes off to affect the solution itself.
Not enough, because they're weak acid and weak conjugate. Or a weaker conjugate. Okay, why would you do titration? Hopefully you can figure that out after what I said.
So it's fine.
Find
So
the pH.
Nope.
At the beginning you said if there was a missing concentration.
Yes.
Determining the
Oh.
Find the concentration of some unknown concentration.
It's right there.
I mean, you could just use like a indicator or a pH meter to find the pH of whatever you want. A titration specifically used to be able to figure out some unknown concentration. Because a lot of times you will get some acid in some, if you were working for a company and you saw, I get this acid when I do this reaction, but I don't know the concentration of it. And so that's what they would use a titration for. Okay, so there's the equation that I put on the board earlier. You guys have that in there?
Yeah.
Okay, good. Let's use it. You could really say M1, V1, M2, V2 if you want. Because it doesn't matter if I take the known and I put it over here versus if I put it here. As long as you have the two things that go together and keep them together, that's all that really is important. Okay? So it says, you did a titration, and you found that 52.7 milliliters of a known concentration was used to titrate, and 76.9 milliliters was the solution of NaOH that you had. Use that information to find out the concentration of that particular base. So I'm going to go ahead and say this is probably my known, right? I could put it on the other side, but let's just actually put it in our known. So what is our known molarity?
2.13.
Okay, our known molarity is 2.13. What is our known volume of that molarity?
22.7.
Now, molarity is usually in, volume is usually in liters, right?
Oh.
Okay, but they're just going to cancel out here. So I can convert both of them to liters, but the ratio would be the exact same. Since they're just going to cancel out in this equation, we do not need to change them. If this was milliliters and this was liters, you would have to convert one to the other. Does that make sense, everyone? Okay, and you'll see how they're going to cancel out here. Okay. We don't know our unknown molarity, and we do know our volume. So you see if I divide by that 76.9, that those two milliliters would cancel out. And so if I move these to liters, I'm just moving the decimal right to the left 3 spots for both, which is not going to change your answer. Okay? When you divide by 76.9, what do you get for a concentration?
1.46.
Okay? And it should make sense. I'm going to need more volume of a less concentrated solution or substance to be able to neutralize something that requires less volume and is more concentrated. All right? How much will let you do the next one on your own? This could also be used as a dilution equation. If I wanted to dilute an acid to a certain concentration, I can figure out how much water I need to add to it. What you gotta get?
Number 1.
Number 1?
Yeah, number 1.
Number 1? Did you do it?
My head.
Do you think that's gonna help you on your test?
I usually go back and look at it on my sheet. Get it? I don't get it when
Well, actually, you
Thanks.
just do this one in your head, because it's the only one that makes sense out of the choices.
Yeah. So like here, more volume to less volume, that means this concentration's gotta be a little bit more than that, and no other number makes sense.
Yeah.
3. Is the test gonna be multiple choice like this though?
No.
That's how I figured it out.
Oh,
serious.
I have, yeah, that's it.
What you gonna do this one? See if you
Number
can
one.
maybe do this one in your head.
Yeah, number 1, I did it.
Didn't you say when
Okay.
you put it in yours?
You're so rude.
No, you
Got it.
since your molarity would just cancel out, you would just be left in units of milliliters.
Now.
So the only way you would have to switch one to the other is if they gave you one volume in liters and they gave you one volume in milliliters. Does that make sense?
Yeah, I'm sure about it.
Let's see.
Well, hold on.
It looks like the concentration
Oh.
goes down, so I'm going to have to increase the volume by about double.
Wait, what? What are you saying?
By
It's-
about.
Oh, I read it wrong.
Yeah, the question's worded weird.
I read it wrong, yep.
Oh, nice.
Yeah, I read it wrong.
Yeah, so did I. Yep.
These two go together, not
Yeah.
these two.
Yeah. Okay.
Okay, looks like the concentration goes up, so then the volume's gonna go down by about half.
Yup.
So probably number one.
Yeah. Okay.
You should have made this.
What was that?
Just like that.
Plug it in.
I mean, you can just plug it in. So the thing, so what the mistake I made right away, and it's a mistake that happens, is you think that, oh, here's my first molarity, here's my first volume, so they have to go together.
And
Read the context of the problem. Even Mr. Kramer doesn't always read the context of the
we should
problem.
watch the context.
Okay? Okay, you could have plugged into the equation, we just tried to do it conceptually. You can get that 18.1. Alright, this one's a little trickier. I'm going to work through this one with not a lot trickier, but that's important to know. Okay? This is a strong acid. This is one of my strong bases, so we know they completely dissociate. However, this breaks apart into twice as many hydroxides as this will break apart into hydrogen. So, they say, according to this equation, adding 38 milliliters of 1.5 times 10 to the negative 2 molar barium hydroxide, solution can neutralize 20 milliliters of hydrochloric acid. What is the concentration of hydrochloric acid? So, I'm going to write this so I don't have to freeze it. Milliliters.
Why is it twice?
Let's not read it that way. This is barium hydroxide.
They're what? They're rebels. Yes.
Okay, so I got 38 milliliters of that concentrated barium hydroxide, and I know that it neutralizes 20 milliliters of HCl. Now I'm gonna freeze this so that I can have a little bit more room to work. Is that cool?
No.
So I'll write the equation here. BaOH2 plus HCl. And then the rest is not really important.
Oh.
Okay?
Until advanced.
We actually spend about a whole quarter on acids and bases in equilibrium.
See, yeah, I told you.
We do a lot of equilibrium acids and base stuff. Okay. Now, this is the concentration. Okay? This is the concentration of barium hydroxide. So I'm just going to put over here quickly. When I put barium hydroxide in, it completely dissociates into 2 OH minuses. So really, the concentration of the thing I'm desiring is the OH minus, right? Because that is what reacts with the hydrogen, yeah?
Yeah.
The part that neutralizes the acid is the OH. And since this gives off twice the amount of OHs as a regular base would, I'm going to have to take this number and do what with it? Multiply it by 2. Okay? So really then, what I have is, what is that going to be, 3 times 10 to the negative 2? Probably correct. Yep. At 38 milliliters. That's my volume. And I'm not going to multiply this by anything because it's only 1, so I don't have to do anything with that. And now you can solve. Alright, so the really only tough thing you could potentially see with the titration equation is if they give you the concentration of it combined, then we have to make sure that it doesn't give off more than 1 of something. Okay? And the only one that will do that is a base. Your acids always give them off 1 at a time. And it's actually, there's only 3 culprits that will ever do it. It's these 3 guys with OH. Those are the only 3 guys that will ever give off more than 1.
So you know that you have to multiply it by 2 because of that subscription.
Yep.
What about 2 in front of the aces? No, that's not important.
That's just to balance it. Alright, last thing, buffers.
What was the answer?
0.057.
Okay.
Yep. 0.057. Sorry, I figured at this point you guys could do the math.
Yeah.
Once
Yeah,
I plug it in.
I
the
just
rows.
forgot my calculator.
What? Not one of the rows. I wasn't roasting her, I was just saying. Yeah, you gotta check.
I have.
Just trying to save my name on that one because it wasn't a row. I was just trying to say why I didn't give the answer. Okay, here we go. Last thing.
The board is so clean, except for that one little. Thank you.
Okay. So what does it say buffer does?
Resist pH changes.
It resists the pH change. How?
We'll find out.
The really conceptual why of this, we probably take a couple weeks to go over this. But let me try to give you the simplest version of this. What a buffer is it's a weak acid or a weak base with its conjugate. Alright? So let's say I have this is my weak acid. Right? It would break down into H plus and F minus. Right? So this is a weak acid, and this is the conjugate base. Okay? What buffers are is they're usually a weak acid with its conjugate. Okay? They have equal concentrations of both. And so what ends up happening is I can take a strong acid or a strong base and I can throw it in here. If I put a strong base in this buffer solution, the weak acid will react with it. And what it actually does then is takes the strong base and converts it into a weaker base. Okay? And if I were to take a...
I don't understand.
What? You don't know what strong and weak mean?
No, my brain just didn't catch up.
What did you do?
Second.
Yeah.
Look at the second.
If I take... Alright, let me slow down. If I take a strong base and I put it in this solution,
Where?
okay?
In the solution.
In the solution, anywhere in the solution.
You just add it,
Right,
okay.
I have a beaker of a buffer, and I pour in a base into that beaker.
But you're not putting in the equation.
Yeah.
Okay.
I mean, I could show you the equation of the reaction if you wanted me to. You want me to do that?
Okay, yeah. Okay.
HF plus NaOH. That will produce H2O. And NaF, well, actually we'll keep it in its ion form. And F minus is the weak base that got produced instead of having the strong base. Okay, this will actually be in F minus form. And so what it did is it took the strong base, which is going to do more damage to the pH, right? Won't a strong base change the pH a lot more than a weak base will?
Yeah.
Why?
It's strong.
Because it's going to give off more hydroxides. This isn't going to react that much with water because it's weak. Okay? Same thing can be said if I add a strong acid. The base of the buffer will react with it, and it will buffer it. When it says it resists a change in pH, it does not mean that it won't change at all. It just won't change drastically. What I'm saying is, if I took a strong base and I just put it in water, you would see a drastic change in pH. But if I put it in a solution that had a buffer, it would take that strong base and convert it to a weaker base, which isn't going to affect the pH as much. Your blood has buffers in it. God is a genius in coming up with buffer solutions, because your blood has to be in between a 7.35 and a 7.45 pH range. If it's in you above or below, you will die. And so your blood has a buffer in it, okay, that if acid, could you by working out, get lactic acid in your muscles and get some of that in your bloodstream? Very possible, right? Now, if you didn't have that buffer in your bloodstream, that would cause your pH of your blood to plummet downward. Okay? And there's a lot of things that you eat that, yeah, they go in your stomach, but can they permeate through walls and things like that and eventually get in your bloodstream? Yes, they absolutely can. And so your blood has to have something in it to cause it to stay in a pH range, because if it changed too much, I don't know if it's the red blood cells or something that would, you know, blow up or something if the pH, I don't know why the pH has to be at that range, because I don't have a greatest biology background anymore. Okay?
Is that why people get drunk?
To what?
Because the alcohol.
What
is in
alcohol?
the bloodstream.
Good question. I don't know.
I think it just affects how your brain.
I'm not sure it does it. I'm not
Like, why do they
sure.
call it blood alcohol?
I'm not.
Oh, because it's alcohol. It's just-
I'm not sure it's either, but I don't know off the top of my head.
Your
Okay, let me
brain's
finish though.
consuming blood.
Okay? I want to make something very clear. Stop. Okay? There's a very basic thing here that I gotta finish. Okay? When I say it resists a pH change, it does not mean that it stops it from changing at all. It also does not mean that it makes it neutral. What it means is that it keeps the pH pretty constant.
Speed bump.
Okay? So maybe instead of the pH going to 20, or not 20, to 12, maybe it just bumped up to 7.37. 7.3. Okay?
Alcohols.
Alcohol, I thought it's because alcohol's going into your blood.
But I'm just wondering why. So maybe that's why if you drink too much, it would kill you. I don't know.
No, I'm saying why you get people get drunk is because their brain's constantly getting.
Okay, and all of this is explaining what I was explaining on the board. So you have it in written form. This is why advanced chemistry is my real class to teach. Because all those questions you guys have, I
So the reason that you don't close stomach chemistry is that so it's taken. It's a question.
No, I have to first introduce the stuff before I go deeper.
Oh, as far as
What? Why you don't keep every single paper because it's done?
Like,
how much
Physics is harder than chemistry, but not as hard as advanced.
so like, if I don't want to plummet my grade, but
Don't take both.
I'm
I don't think
thinking
you'd
Matt, you take both.
Both in 1 year.
What do you like math?
The answer is no.
You like
Physics is more
math.
math.
Okay.
Wait, physics is more math than advanced chem? Take it in that.
How do you get it?
I don't know.
Wow.
You almost shot my tooth off.
Holy cow.
Hey, I already had it once. I didn't think it was actually like prime good.
Dude, wait, I want to shoot someone.
It's extremely rare.
Whose is this?
And then tomorrow, not tomorrow, Monday during class, you'll take this chapter
You
test.
took your head.
Okay?
And then you were like,